Hey guys, it's Neil, and for my project, I implemented bounding volume hierarchies, a data structure for accelerating the raycasting process for rendering objects. So bounding volume hierarchies take a set of primitives like a triangle in an OBJ model, and it partitions the space recursively to group objects closer and closer together. And the idea is that at every node, if it's not primitive, it can be split into two children bounding volumes, and those contain primitives on and on. So when we cast a ray and it doesn't intersect with the bound of one of these nodes, we can immediately eliminate the whole sub array and all triangles within it, and kind of go on without having to consider all those triangles individually. And then one kind of benefit is that by seeing the order in which we intersect with the bounding volumes themselves, we can first check the closer bounding volume before the second child, which is more likely to give us a hit and prevent us from needing to go any further. So like if you intersect with the first volume, you're guaranteed to not have like the any intersection in the second volume will have like a t value greater than your first intersection, which is super nice. Looking at the code over here, I have a BVH abstraction that abstracts over the leaves, which are primitives, and the nodes, which contain children. Here are implementations of the leaves, and then for the nodes, there are different heuristics, so I encourage you to kind of test out different defines, to test out different algorithms, and see how many ray triangle intersections are done. The output is over here. It's a bunny in the background, which is a metal material, so it itself is reflecting back into the scene. And as you can see over here, the different spheres are also reflecting the bunny. So there aren't just rays coming from the origin, they're coming from all directions. Back to the presentation. So in the leaf case, where we just kind of consider a conglomerate, there's a lot of intersections required. It's a number so big I don't even know right here. But when we implement the BVH node and the like naive algorithm, you can see there's a massive speed up of roughly 30%, and there's only 1 billion ray triangle intersections being done. So it drops to nearly 0.1% of the original. Now, the actual runtime isn't 1% of the original because we are making a trade-off where we have to do more axis-aligned bounding box / ray comparisons instead of the ray triangle intersections. But those are so much cheaper than the triangle ones that it's still worth it at the end. Now, one thing that I kind of messed up initially was that my base case was 20 triangles, which is a lot. It turns out that if you go to 5 triangles, you do get a minor speed up. So the number of ray triangle intersections drops by nearly half, but at the leaf nodes of a BVH, they are so fine that we have to perform so many extra AABB tests that the amount of work is roughly similar. So the speed drop isn't nearly as profound as like a half. Now, alongside, when constructing your BVH, the way you select the splits is really important. So in terms of what axis to split on, we choose to split on the axis that is the longest. So by making the bounding volumes more cubical, the probability that they intersect with a ray, with any random ray, decreases. So it's like the surface area to volume ratio. So always incentivizing it to go towards a cube is better, but it's not always the case that that's required. So selecting splits for like D objects, they're D-1 splits, and choosing where the split should be is hard because it's not easy to see in foresight what is this best split. We can do kind of a naive median approach where we take the median point and split on that, but there are kind of heuristics we can use, such as like the surface area of the children that's produced, the intersection volume of the children that's produced, the actual volumes of the children that are produced. So in this next slide, as you can see here, there are like 4 different heuristics that we looked at for producing quote unquote optimal splits. So originally it was the naive median algorithm where we take the median of the centroids and that is our divider. But we can pay a little bit of an extra price to get something that's more likely to be better. For example, in the max children volume heuristic, we take the minimum maximum volume of a children for a given split. So the idea is to incentivize very small volumes. But in some one useful thing is that if the more segregated the children are from each other, the better, the more likely it is that the ray will only intersect with one of them. So by incentivizing minimum intersection volume, we can incentivize them to have very little overlap, the two children. But in tessellated objects such as OBJs, it's not as easy to achieve this. So we can also use IOU, which is the area of overlap over the union, and use that as a heuristic to incentivize small volumes, but even smaller intersections. And on the next slide is kind of results on this. You can kind of test these out yourself on the mock by using the correct defines in the README, and they'll kind of run the test, for a given primitive to point method and a split evaluation heuristic. So the baseline was the naive median with mean centroids, so taking the average coordinate on a given axis and then taking the median of all the centroids. But as we implement heuristics, we see roughly a 30% speed up. And this is super useful because it shows that even though we pay a price initially, the actual quality of the speed of the actual render itself is much faster. Something that I didn't actually realize was that going from mean centroid to median centroid created a huge speed up / improvement. I personally don't know why that's the case, but when going from mean to median, there's roughly a baseline 60% drop in ray triangle intersections required to render the scene. So that's definitely the first takeaway, and applying heuristics on top of that create even better results. It was theorized that like comparing the mean to the medians can produce even better splits, but personally I'd already looked at 8 separate cases, so I didn't want to make the project too big, even this video too big. So paying the price upfront is really useful, especially when we go to higher resolutions. In this case, we're only rendering an 800 by 600 image with 4 samples per pixel, but in the case that you're rendering an 8K image with 32 samples per pixel, the number of rays cast can go from like 3 million right now to like orders on orders of magnitude higher. So in that case, paying a small price to set up your BVH will pay off dividends when you actually need to render the scene using raycasts. Yeah, so that's definitely the takeaway, and be sure to look at the README. Thank you.